Well, good morning. So last time I asked you to do several things for your homework, and most of you actually did it. You did it on time, so thank you for that. There are a few students who still need to get me some information, so first I want to go through that. So these students that are on this list, I still need your student information. Okay, so if you see your name here, I still need that student information. I will post it one more time in the WeChat group, and maybe a few more times because there's a few of these students that aren't actually in the WeChat group yet. And then I also need several students to verify their attendance from last time. Okay, if you've watched the video, I told you how to do that. So you need to send me an email with some information. Okay, now, as I said, most of you that are here now, you did what I asked. So I would actually ask if you know any of these students, if you could just tell them they need to do this. And the reason I'm telling you this is because in my experience, if students start out and they don't do what I ask, they get behind very quickly and then they wind up failing the class. Okay, so please help me out. And actually, after today, I am not going to chase after students. I'm going to leave you each up to your own devices. You need to be responsible when I tell you to do something, and if you don't turn stuff in, I'm going to let you not turn it in. So I'm just trying in the beginning to make sure everyone's connected, but really it's not my job to always say, oh, you didn't do what I asked you. You know, you didn't put your name in the chat last time, or you didn't send me the email. So last warning, these students need to give me that information. Okay, so now let's actually look at the homework that everyone did last time. We talked about significant figures. And so you had to first do the math, and so I've done the math here, and now we need to talk about the significant figures because all of these are wrong. Okay, so the first one, almost everyone did correctly. That's an addition, so we have to look at the number of decimal places. This has 5, this has 2, so my answer should have 2. So your answer should be, your final answer would be 77.04. The second one, also most people did correct. Again, same rule, 2 decimals, 0 decimals, so the answer should have 0 decimals and should be minus 51. Okay, C and D, a lot of people had trouble with. So here's the math. So notice this is 99,947, a big number. Now, significant figures, this is a different rule. We look at the number that has the fewest, okay, not after the decimal. So this one has 5, this one has 4, so my answer has 4. So some students say, oh, well then I'll just write 99,950. Okay, but remember, you cannot have a number that ends in 0. We don't know, is that significant or not? So you have to use exponential notation. So this one should be 9.995 times 10 to the 4th. Okay, D, a lot of people had trouble with the math. And again, the problem is you're not paying attention to the number system. Remember last time I told you a comma means this is a big number. This is not 78.132. This is 78,000. Okay, so when you do the math, the answer should be 31,252.8. It's a big number. Okay, now, so that was the first problem. A lot of people aren't paying attention to the difference between a comma and a decimal point. Second problem, significant figures. Okay, this one has 5, this one has 3. That means my answer should only have 3. And again, the only way to do that is to use exponential notation. So this one should be 3.13 times 10 to the 4th. Okay, E is a combination of everything. So we first do this subtraction, and so this part would have three significant figures, no decimal point. This one has 2, this one has 4. So my answer should have 2. So you should have 1.2 times 10 to the minus 1, or 0.12. Okay, the log, that's a different rule. So remember, this one's a little bit harder. So that one, we have to look at how many significant figures here, and then we need that number after the decimal point. Okay, so 2 here means 2 after the decimal. So that one should be 4.74. Okay, and then finally, G is an inverse log. This is probably the hardest one. So remember, when we've taken a log, the significant figures are these behind the decimal point. So when we had 3.47, the significant figures are right here. So that original number had 2 significant figures. So that means your answer should be 3.4 times 10 to the minus 4. Okay, so those are the correct answers you had. Now, when we have a quiz or a test, I'm not going to ask you a question like this, that's just significant figures, but you will do calculations. And anytime you do a calculation, when you get all finished, you need to go back and look at the significant figures, okay? So I expect you to pay attention to this, and if you don't, you're going to lose points, okay? So you do need to pay attention. All right, are there any questions on any of these? Okay. Next, I mentioned quizzes. We will have probably 4 quizzes in this class, and those will usually be about 30 minutes, and they'll always be at the beginning of class. Now, because some of you are in China, but many of you are not in China, and you are in countries where it's 2:30 or 3:30 in the morning, what we're actually going to do is have quizzes at 2 different times. Okay? So for those of you in China, quizzes will be during class at 8:30. And if you are in China, you must take the quiz at this time. This is your class time, so that's when you have to take it. If you are not in China, then we will have a second time for quizzes, and those will be at 2 o'clock in the afternoon China time on Friday afternoon. And for most of you, that's around 8 o'clock or 9 o'clock in the morning, so it's close to class time. Okay, so if you're not in China, you can actually choose which is better. Some of you have said, oh no, I can come to the lectures live, and you might prefer 8:30, but others have said, no, that time is bad. You know, it's really hard at 2:30 in the morning. So you can choose. And for everybody, the quiz will be on the RAIN classroom. And what I'm going to do is actually make a second RAIN class for those that are outside of China, so that, because the quizzes are timed and they will be locked after the time for the quiz to be over. So the people that are outside of China will actually go to a different RAIN classroom to take their quizzes. And that way everyone can take the quiz, and it'll all be timed, and you know, it'll work the same way. So everyone will need to let me know when you're going to be taking the quizzes. This will actually be a question in your homework, and I'll tell you later how you're going to give me the answer to that. Now, I just said if you're in China, you have to take it at 8:30, but I want everyone to answer this question because I want you to acknowledge, yes, I know what time I'll be taking the quizzes. And we won't have a quiz for several weeks yet, but I'm trying to get everything prepared and set up now, okay? So that's something to look forward to. Okay, so let's go ahead now and move on to chapter 1. We're going to finish that today. So last time we talked about significant figures. We've already reviewed that homework. I also gave you a lot of words last time that I said you need to know these words in English, know what they mean, what their definition. The first 2 we talked about were qualitative and quantitative analysis. So if I ask, oh, what is qualitative analysis? You should be able to tell me, what is it? answers the question, what is it? Okay, what is quantitative analysis? Well, that answers the question, how much is there? And if I ask you that question on a quiz or a test, really all you have to say is, what is it? Or how much is there? You don't have to give me a long, complicated answer. That's all you need. What is it? How much is there? We also talked about last time these 4 words, sample, analyte, matrix, and interference. You should know what all of those are because I'll be using them frequently as we talk about methods. We talked about calibration curves and the general method of making a calibration curve. And if you remember, I said a calibration curve, the general curve, what do we put here? That's always the signal from my instrument, and here, concentration. And almost always these will have a linear response. And we talked about blanks in a standard. Remember, blank is the thing that has everything that your sample has, but no analyte. So the response, the signal should be 0. And we talked about standards, this common abbreviation. Remember, a standard is something that I have a known concentration. So you should know those 2 words. And then we talked about precision and accuracy. So you should know what those 2 are. Okay, remember, precision has to do with how reproducible a measurement is. And the common way to measure precision is standard deviation. Accuracy, remember, is how close I am to the true value. And we talked about errors and the types of errors, and the error will tell you about the accuracy of a method. Okay, all of that was from last time. So today now, we're going to talk about these other terms. There are several other terms that we use when we want to evaluate a method. We use these terms to compare methods, to tell us how good a method is, and different aspects of a method. So we want to make sure we understand each of these. So the next thing we're going to talk about is the signal and the noise, which are actually related to the precision and accuracy. I should say the precision and accuracy are related to the signal and noise. Okay, so every instrumental measurement has 2 parts. So the first part is this thing we call the signal. So remember last time I said these instrumental methods, we use some kind of energy to stimulate my system. I want to study this system and I want to know, what is it? How much is there? So I use some kind of energy that then gives me a response. It gives me a signal, and that signal tells me, what is it? How much is there? So we have the signal and we use S to represent that. And then we also have this thing called the noise. Now, the noise is something that is bad. We don't want it. And notice it says it's fluctuations. So noises sometimes will be high, sometimes they'll be low. But we don't want them, but it's fluctuations in the signal. And noise hinders, it's bad for both precision and accuracy. Okay, so here I have a sample and I'm measuring it, and notice I have a blank. And it gives me some kind of response, and then I have the response from the sample. So the difference between the sample response and the blank response, that's the signal, okay, that I'm measuring, this S that I'm measuring. Now, ideally, that blank should be 0. Okay, remember from last time, what is a blank? Well, a blank is the thing that contains everything that my sample has, but no analyte. And remember, the signal is supposed to come from the analyte. So if there's no analyte, the blank should be 0. But in fact, the blank is never 0, exactly 0, all the time. That just doesn't happen. There's almost always going to be a small signal that you get from the blank. So that signal you get from the blank is called a background or a baseline. Okay, so these are 2 more words you should be familiar with, the background or the baseline. That's the signal from the blank. And again, it should be close to 0, but it will never be exactly 0 all the time. Now, usually what we'll try to do is actually take that baseline and adjust it to 0. A lot of times there'll be a knob that you can actually pull the baseline down to 0. But even then, it won't be exactly 0 all the time, okay? Because there's always going to be some plus and minus differences. So quite often you might get a response that looks like this A here. Now notice this baseline here, it's nice and smooth, but there's a little bit of variation. We want it to be close to 0 and we'd want it to be totally flat, but in real life it's not. There's always some noise, some fluctuation. And then this right here would be the signal from my analyte, and we call that a peak. Then we look at situation B. Now notice B has a lot more noise than A, but we can still clearly see my signal. Okay, but now look at C. Okay, notice here, this baseline is very, very noisy. It's almost impossible to see that that's a peak among all this noise. And this, of course, is what we don't want, but sometimes that's the situation. Okay, so some different ideas of what signal and noise might be looking like. Okay, so let's talk a little bit more about the noise. As I said, the noise is random, changes with time, and it's not related to the signal. So notice this noise saying B, the noise sometimes positive, sometimes negative. It's always changing, but it has nothing to do with the analyte. And the noise can obscure, it can hide my signal. And as I said, it's bad for precision and for something called the detection limit. So for example, if I take my sample and I get something like this, and then I say, okay, where's the peak for my analyte? You look at that and, oh, this is pretty noisy. Well, there might be a peak here. There might be one here, but it's really hard to tell. So if you have a lot of noise, it can sometimes kind of hide your signal, obscure your signal, so you can't see it. Okay, so the signal and noise, we've said that we'll use the symbol S for signal. Now, how do I actually measure the signal? Well, the signal is just the average value of your peak. So you would go and measure your analyte many different times. Up here you would get this value, and then I'd measure it again and again, and then I take an average. Okay, so the signal is just the average value for your analyte. The noise, remember, the noise is this variation down here. And how can I measure that? Well, again, we're going to take my sample and measure it many, many times, and I'm going to look at this baseline. And because sometimes it's positive, sometimes it's negative, I can actually treat it with math statistically. And in fact, it turns out that if in almost all cases, your noise is actually equal to the standard deviation of your measurements. Okay, so just take your sample, you measure it many times, you get the average value, and you get an N, a value for, or you take the standard deviation of the average value, and that's your noise value. Okay, so that's signal and noise. All right, now a question. I've talked about signal and I've talked about noise. So which one of those do you think is most important for your measurement? The signal or the noise? To have a good measurement, what's more important, the signal or the noise? Well, you might say, well, the signal, that's most important. So let's say I have this case where, I have this signal that looks like this. Really hard to draw nice peaks with my mouse. Okay, and we say, oh, that's a great signal. Okay, now, here comes the noise. Okay, so if you have noise like this, you're not going to be able to see this signal. And we say, oh, okay, well, it must be the noise that's important. Okay, so I have this measurement, and now I have this really small noise. Okay, now here comes my signal. Oh, it's really small too. Okay. In either case, I cannot see my signal. So in fact, it's not the signal or the noise that's important. It's actually both. It's actually the ratio of the signal to noise. So we talk about something called the signal to noise ratio, where we just take that average value divided by the standard deviation. That's actually 1 over the relative standard deviation. And we get this thing called signal to noise. So let's look at an example of how we might do that. So here's a sample I've measured, and notice they've got the signal value up here. This one has a baseline that's not 0. And then they've measured the noise up here. Now, I told you, often we use the standard deviation to measure noise, but you can measure it directly, like they have done in this example. You can also measure noise down here at the baseline. That's actually more common, to measure the noise here. Okay, so we could calculate the signal to noise. So we take that signal minus the baseline, because that's my true signal, divided by the noise, and I get a signal to noise ratio of 7.5. Okay, now, is that a good signal to noise? Well, if you look at this, can you clearly see that signal? Yeah, you can. So this would indicate, 7.5 is probably an okay signal to noise. That's not bad. With that signal to noise, I can see my signal with the noise. So let's look at another example. This has a signal to noise of 1. Now, can you see the signal here? Can you tell me where the peak is here? No, absolutely not. This is a terrible signal to noise. If your signal to noise is 1, you can't measure the signal. We can't even tell where the signal is. Okay, so what is good? What's bad? Well, here's some examples of different signals to noise. So notice if it's less than 2, we really cannot tell where there are peaks at. So obviously, less than 2 is going to be a poor signal to noise. This one, 2.8. Almost 3. Notice here we can just start to see this peak right here, but it's still a very hard measurement. By the time I get to 5, I can clearly see there's a peak. It's still pretty noisy, but clearly there's a peak. And here at 17, now it's clear there's a peak. So the general rule is if your signal to noise is less than 3, you cannot detect the signal. You cannot say, that peak is from my sample. So, this one, 2.8, we really cannot accurately say, that's a signal from my analyte. So we need a signal to noise of at least 3 to detect my signal. Now, that doesn't mean I can detect it really easily, but I can at least say, yeah, I'm pretty sure it's there. Okay. Now, where does this noise come from? It's obviously a big problem. Well, most noise is indeterminate air, and it comes from things like chemical changes, changes in temperature or pressure, humidity, the changes of light intensity. Inside your instrument, it has to do with random motion of electrons. There's electrons in your instrument moving through it, and some electrons have higher energy, some have lower. Electrons that have to cross junctions, even the electromagnetic radiation that's all around us from power lines and phone signals that can be picked up by instrument. So all of these are things that cause noise. And as I said, these are indeterminate. Now remember, indeterminate, those are the things that I can't get rid of. They're always there. So we're always going to have noise in every measurement. There are some ways to try to make the signal to noise better. You can try to make your signal higher, or you can try to make the noise lower, or you can try to do both. And there's actually many ways to do this. I'm just going to show you 2 really quickly. They can be divided into 2 categories. So hardware, where you're using something physical to change it, or software where you're actually using math to get rid of the noise. So we'll look at one example of each, but there are many more ways to do this. So hardware would actually be building some kind of a filter. So you've got resistors and capacitors. So you take this noisy signal we see up here, and after it goes through this filter, it gets smoothed out. Okay. You can also do this with software. There are math functions you can use to smooth these out as well. Another way to improve signal to noise is something called signal averaging. So this is actually where you take multiple scans and you add them together. Scan, I showed you this earlier and I said, oh, is there a peak there? And we said, well, maybe, but we can't be very sure. The signal to noise is poor. But remember, signal is always positive because that's from your analyte. Noise, sometimes positive, sometimes negative. It's random. So what that means is if you add multiple scans together, your signal is going to increase more than your noise. In fact, your signal to noise will improve the square root of n times. So you can clearly see this. If I add 50 scans together now, this has a much better signal to noise, and 200 better still. So the more you add, the better you can make your ratio. And this is actually used in some methods when you can, this one scan, if I can do that very quickly, if that one scan takes me 1 second, then it's very easy to add 200 together to improve my signal to noise. But let's say that one scan takes an hour. Well, then signal averaging is not very practical. So it kind of depends how long it takes to get the measurement. Okay, so that's precision and accuracy and errors and signal to noise. Okay, now we still have these 5 other parameters to talk about. These will be much shorter. We spend a lot of time on precision and accuracy. These we're going to go through much quicker. Okay, so the first one we're going to look at is something called selectivity. So selectivity, and for all of these, you should know their definitions, what they are. So this is the ability to determine an analyte in the presence of interferences. So remember last time I talked about sodium and potassium. They have similar chemistry. Often they react the same way. So sometimes if your sample has both, it's very hard to get the signal from just the sodium. So if I say a method is selective for sodium in the presence of potassium, that means I can measure sodium with potassium there. Okay, bromide and sulfide is another example. If my sample contains sulfide and that interferes with the measurement for bromide, then that method is not selective. Okay, so a couple of kinds of interferences that you might run into. One is called spectral interference. So here in this case, we're trying to measure the concentration of manganese. And so I'm reacting it with X, and I'm getting this peak. It absorbs. And I'm going to measure the absorbance, and that's going to tell me about the concentration. But if my sample also contains iron, the iron will also react with X, and it will also absorb. So when I'm trying to measure this absorbance here, notice I get the signal from the manganese, but also a signal from iron. And I see them both together. So we would say in this example, this method is not selective for manganese in the presence of iron. Another example, matrix interference. So here again, I'm measuring manganese, and now we know the concentration is 1 part per million, but notice I have it in different matrices, okay, different types of samples. And when the sample contains very high concentrations of sodium, notice the signal's not the same. The signal decreases as the concentration of sodium gets very high. So again, we would say, oh, this method is not selective for manganese in high concentrations of sodium. Okay, so that's what we mean by selectivity. All right, the next one is sensitivity. So sensitivity is, can I distinguish between small concentration differences? So can I tell the difference between say 0.1 and 0.2? Or can this method tell the difference between 0.001 and 0.002? Now, if it can do this, that's much more sensitive than if it can only do that. So this method, sensitivity measures, what concentration can I tell the difference between? So there's actually two factors that determine a method's sensitivity. Okay, the first is the slope of the calibration curve. Okay, now remember, a general calibration curve, what goes here? Signal. And what goes here? Concentration. Okay, and so I'm going to get some line. Okay, so that slope of the line is actually, notice, is the change in the instrument response. It's the change in the signal divided by the change in concentration. Okay, so that's one factor that determines sensitivity, and we'll look at that on the next slide. But let's get the second factor. So the second factor is the precision of the measurement, or the reproducibility. So let's explain these a little bit more. So we said the slope affects the sensitivity. So notice here, when I have a very low slope, m is a small number. So if I have a change in concentration that's this much, notice the change in the signal with the low slope, it's very small. Okay, but now I have that same change in concentration with a large slope. And notice this change in signal, much bigger. So the bigger M means the method is more sensitive. I get a bigger change in signal for the same change in concentration. Okay, the other thing we said, precision. Okay, so here we have a high precision and a low precision. So notice high precision, we measure it many times, we get very close to the same number. We get a small standard deviation. So in that case, notice, if my signal is in this range, then I know the concentration within a small range. But if I have a low precision method, so very noisy, big standard deviation, notice that same signal, I know, oh, well, the concentration is between here and here, so it's a big range. Okay, so that's a low sensitivity method. Okay, so for a sensitive method to be able to tell the difference between these smaller numbers, I need two things: a big slope for my calibration curve and good precision. Okay, so that's sensitivity. All right, the next term is a very important term that we'll talk about. It's called the detection limit, and the abbreviation is LOD, which stands for limit of detection. Okay, so same thing, LOD, detection limit. You should know it both ways. Both are commonly used. So what is this? Well, this is the minimum quantity, the minimum concentration that you can detect. Okay, it's that place where I can say this peak is definitely from my analyte. It's not from the noise. Here again, it's a very noisy signal, and we look at these peaks and we say, oh, are those from the analyte, or is that part of the noise? Okay, so the detection limit, that is that smallest quantity when I say, oh, that is from the analyte. So the detection limit can be determined by taking the standard deviation of the blank. So you get a blank. Remember, that's the sample that has everything that your sample has, but no analyte. And now you're going to measure the signal for the blank many, many times. And you're going to get the average and the standard deviation. So the detection limit is then defined as the average plus 2 standard deviations or plus 3 standard deviation. Now, what's the difference? Well, something called the confidence level. So the confidence level is a level of risk that you're going to have a false answer. So, for example, if you have a 2S, that's 95% of the time you're right. If you have 3S, 99% of the time, you're right. Now, if we have a test and you get 95%, most of you would be very happy with 95% on a test, and 99, wow, that would be great. But let's think about it. I say, well, I got my water here in my thermos, and I think my water might have poison in it. And if I drink that poison, I'm going to die. So you go to the lab and you come back and you test it and you say, well, I'm 95% sure there's no poison in your water. Do you want to drink that water? No. Even if you say 99%, that's better, but still, I'm not sure I want to drink the water. So, for some measurements, we really it's important that we're sure. Okay, now, this 2 standard deviations and 3 standard deviations, that's actually equal to a signal to noise of 2 or 3. Okay, now, normally we're going to use 3S for our detection limits because 3S is a little bit surer. Now, it doesn't mean that we're 100% sure. In fact, you can never be 100% sure. You can be better than 99%, but we can never be 100% sure that there's not poison in my water. But we might be able to be very confident that there's not a level that I can determine, and that there's not a level that will harm me. Okay, so the detection limit. So again, I said that this 2 standard deviations and 3 standard deviations is equal to a signal to noise of 2 and 3. So, this one that's less than 2, this would be like looking at this and saying, oh, no, it's not there, or yes, it's there. And, we've talked about, no, I can't do that. 3 is close to this one, and here we can be pretty confident that that analyte is there based on 3. Now, I can't really measure this, but I can look at that and say, yeah, I'm pretty confident there's a peak there. Okay, so that's what the 3 standard deviations means, the 99% confidence level. Okay, so remember the process. I take my blank, I measure it several times, I get an average, and I get a standard deviation. So that average for the blank, that would be this value. And some of them are going to be higher, some of them are lower, so you get this distribution. So this limit of detection that we're talking about, that's that average plus 3 standard deviations, that's that number that would be right here. Okay, and again, the detection limit tells me the analyte is present, but I cannot measure it. I can tell you, oh, your analyte is there, but I can't give you a number for how much is there. All I can do is say, yes, it's there, or no, it's below the detection limit. Okay, so that's detection limit. All right, the next thing on the list is what we call the limit of quantitation. So this is now the level where I can actually make measurements that are reliable. These are numbers you can trust. Okay, so that is defined as 10 times the standard deviation, and that is equal to a signal to noise of 10. So again, you would take a blank, measure it many times, you get the average, you get the standard deviation, and now we get this LOQ, the limit of quantitation. Now, what if my signal's between the LOD and the LOQ? Well, then my analyte can be detected. I can say the analyte is there, but I cannot accurately measure it. All I can say is it's there, but I can't give you a number that we can trust. All right, so let's look at an example. So I have a blank now of something, and I measure it 10 times, and my average is 0.025. And my standard deviation is 0.0063. Okay, now I want to know, what is the lowest signal that I can detect? And it's the smallest number I can detect. And then, now I have a sample. and the sample has an absorbance of 0.072. And I want to know, can I measure that or not? Okay, so how would we do this example? So notice first, what information have they given us? What have they given us? Well, they have given me the average, and they've given me the standard deviation. All right, so the first thing, calculate the lowest signal I can detect. That's the LOD, the limit of detection. Okay, so remember, and they asked for 99, so the limit of detection is just this average plus 3 times the standard deviation. So I put the numbers in and I get 0.044. This is the limit of detection. This is the lowest number that I can detect. All right, now the next thing is I have a sample and I get a number and they say, can you measure this? Okay, now remember that question, can you measure this? That is related to the limit of quantitation. Okay, so got this number. And so I'm going to put in again the average 10 times and I get 0.088. All right, now the sample we're trying to measure is 0.72. So can I measure that? Well, we look at this number compared to this number, and this is smaller than this. So the answer is I cannot measure it. Okay, now can I detect it? Yes, it's bigger than this. I can detect it. So I can say this analyte is there, but I can't give you a number. All I can tell you is it's there. Okay. I can measure, or I can detect it, but I can't measure it. So going back to this figure, I just put these numbers in again so you can see. So I had the blank, and this is the average value for the blank, 0.025. It's close to 0, but not always 0. Okay, then the plus 3 standard deviations, that's this number. So right here, this is the detection limit. Okay, then 10 standard deviations, that's right here. That's the limit of quantitation. Okay, so now when you get a sample, if you get a number that's anywhere out here, you can measure that. If you get a number that's in here, then you cannot measure it. You can say, you can detect it. You can say, yes, the analyte is there, but I can't give you a number. And if you get a number that's down here, you cannot even detect it. So you say it's below the detection limit. I can't detect it. Now, just because you can't detect it, that doesn't mean it's not there. It just means your instrument can't measure it. It can't see it. Okay, so limit of detection, limit of quantitation. And again, these are related to signal to noise. So when I'm saying I can detect it, this is when your signal maybe looks like this. You know, yeah, I can see there's a peak, but I can't give you a good number. Okay, signal to noise of 5. That's where you're here in this region. So yeah, I can detect it, but I still can't give you a really good number. And then when you get up here above 10, so this one, that one I could give you a number for. Okay, and then the very last thing on the list is this thing called dynamic range. So this is the range where your measurement is reliable. So we've already talked about the low end, the lowest concentration where I can do a measurement is that LOQ. And what's the high end? Well, the high end is something called an LOL. And the LOL is the limit of linearity. This is where your curve stops being linear. So if you notice here, as we get to a very high concentration, notice the curve starts to curve off. It's no longer a straight line. So this is the upper limit of what you can measure. So the method can measure between the LOQ and the LOL. And ideally, you want this range to be a big range. Notice here it says we want the dynamic range to be a few orders of magnitude. Okay, now, what does that mean? Well, an order of magnitude has to do with expressing things in powers of 10. So if I say something is 100 times bigger, that's 2 orders of magnitude. If it's 1,000 times bigger, that's 3 orders of magnitude. If it's 10,000 times bigger, that's 4 orders of magnitude. So what they're saying is I want to measure a big concentration range. So let's say this LOQ is 10 to the minus 1, we'll say molar, and the LOL up here is 10 to the minus 2 molar. Okay, well, in this case, the orders of magnitude is 1. And that's not very big. That's not a very powerful method if it can only measure between 10 to the minus 1 and 10 to the, whoops, I've got those numbers switched. This should actually, sorry about that. It should have the lower concentration here and the higher concentration here. My bad, sorry. All right, so if I can only measure between 10 to the minus 1 and 10 to the minus 2, that's not a very powerful method. But what if the LOL is still 10 to the minus 1, but this one is 10 to the minus 7 molar? Okay. Well, now that's 6 orders of magnitude. That's a huge concentration range. You know, I can measure between 0.1 and 0.00000001. So that is a much more useful and powerful method. Okay, so when they say we want it to be a few orders of magnitude, that's what they mean. Okay, all right, so that now finishes chapter 1. So we have now looked at all of these different ways to evaluate a method. And as we get into methods in the next chapters, we will often talk about some of these different parameters because they help us understand, you know, what kind of sensitivity do they have? What kind of selectivity? What kind of interferences are there? What are the detection limits? You know, what's the dynamic range? We'll talk about these things as we get to different methods. Okay, so that finishes chapter 1. Are there any questions here before we take a break? Okay, we will go ahead now then and take a break. Okay, let's go ahead and continue now. So we're now turning to chapter 2, which is going to deal with our first chapter on one of the types of methods. If you remember last time, I told you there were kind of 4 categories of methods. The first one was this thing called spectroscopy, and then there was electrochemistry, and then separations and miscellaneous. So starting from chapter 2, we're going to start discussing spectroscopy. So chapter 2 is an introduction to spectroscopy. So what we're going to talk about here is kind of true for all types of spectroscopy methods. So let's start off with a definition. What is spectroscopy? And so spectroscopy can be defined as the interaction of electromagnetic radiation and matter. Often we say EM radiation, or often they just say light, because EM radiation actually is light. So this definition is one you should know, the interaction of electromagnetic radiation and matter. And if you remember, I told you in chapter 1, there's this table that lists all the different kinds of methods and the kinds used to get a different response. And so in that table, the first 6 are all spectroscopy methods. Now in this class, we're only going to talk about one of these. We're only going to talk about the absorption of radiation. But there are methods that deal with emission and scattering and refraction and diffraction and rotation. And there are lots of different methods that deal just with absorption. And we're only going to look at 2, one for molecules and one for atoms in the UV vis. So this is a huge field. We're going to look at 2 small pieces. We're going to look at the 2 most commonly used ones, but there is a lot more. So this is another slide that kind of summarizes the same thing. It just shows you all the different ways that light can interact with matter. And notice light can come out of a sample. We can do what's called transmission, which means to go through, or absorption. And those are actually related. And that's what we're going to focus on. But again, I want you to realize that there are so many other ways that light and matter can interact. You can see all of these in red are different methods that are used. Others of these, all of these that have the shamrock symbol, those are actually part of how an instrument works. Okay, all right, so that's kind of the background of interaction of light and matter. So now we actually want to take a step back and say, okay, spectroscopy is the interaction of electromagnetic radiation and matter. So what is electromagnetic radiation? Well, that's a form of energy that has both wave and particle properties. And it moves through space as a wave, and it actually has both an electric wave and a magnetic wave. But usually for spectroscopy, we usually only think about the electric wave. So we want to do a quick review on this idea of the wave and particle nature of light. So remember, for the wave description, we're thinking of light as a wave. And so we can assign these different variables that I'm sure you've talked about in other classes. So the first thing we can talk about is the wavelength. So that's the distance between peak to peak, or crest to crest. And we use this symbol called lambda to measure wavelength, and it's usually in one of these units, like meter, centimeter, micrometer, nanometer, and this last one, angstrom. These are the two that we will primarily deal with. So you should make sure you know nanometer is what? 10 to the -9, and angstrom next to it. This one you may be less familiar with. That's 10 to the -10 meters. Okay, so we can talk about a wavelength. We also talk about frequency, which is the symbol nu. And so that would be, we take a wave, we take a fixed point, and we see how many of these peaks go by per second. So the units for that is 1/seconds, reciprocal seconds, that's called, or hertz. And you know that the frequency and the wavelength are related by the speed of light. Okay, the speed of light is the frequency times the wavelength. If you're in a vacuum, that number is 2.9979 times 10 to the 8th meters per second. If you're in air, it's a little bit slower. If you want the number with a bunch of significant figures, it's this, but usually we only need 3 significant figures. So we often just say the speed of light in air is 3 times 10 to the 8th meters per second. Okay, so that's the wave description. We talk about wavelength and frequency and speed of light. The other description is the particle description. And that's based on something called the quantum theory. And remember, the quantum theory is the idea that only certain values of energy are allowed. And so we think of light as not being a wave, but as being a particle. And these particles we think of kind of as packets of energy called photons. And remember, the energy of one of these particles of light is equal to Planck's constant times the frequency. And so we measure energy in joules. So if we put together all the equations from the wave nature and the particle nature, we have this. And so when we talk about light and its interaction with matter, we talk most often about energy and wavelength. Those are the most common terms. And that's a little bit of a problem, because we have to remember that when the energy gets higher, the wavelength gets lower. And when wavelengths get longer, energy gets lower. So there's this reciprocal relationship that, kind of makes our brain have to think a little bit more. If we talk about frequency, it's easy because when frequency goes up, energy goes up. When energy goes down, frequency goes down. But remember that energy and wavelength are always different, moving in different directions. Okay, now if we were to take all of the different kinds of electromagnetic radiation and put them together, we get this thing called the electromagnetic spectrum. And so notice here we are going from a high energy to a low energy. And high energy means short wavelengths to longer wavelengths. And so notice the different names for the different types of light you talk about. You should be familiar with these different names in English. Okay, so at the high energy, you should know all these names in English, and you should know the order of energy or wavelength for these. So highest energy are these things called gamma energy. Those come from outer space, have a lot of energy. Then X-rays, that's of course what you use if you go to the doctor, you have to think you broke your arm, you have to get a picture of the bone. Then there's ultraviolet, we will abbreviate that as UV. And then the visible, that's actually the only light we can see with our eyes, and we'll abbreviate that as VIS, sometimes written like this, sometimes all capitals. Then next is infrared, that is abbreviated IR. And then the microwaves, what you would use in a microwave oven, and then the radio frequency. These are very low energy, long wavelength. So you should be familiar with these different names and the order. Sometimes you will see the spectrum written like this, from high energy to low energy. Sometimes it will be flipped like this, from low energy to high energy. So if you see a spectrum, you just need to pay attention to which way they're doing it. Okay, so for the different types of radiation, these are the most common units that are used. So again, for us, we will pretty much only be looking at the methods that use UV vis and visible light. So the most common unit we'll see is the nanometer. We will see some figures even today that use this symbol, the angstrom. That's a little bit older, and so sometimes you'll see that. You should be familiar with what that means. Okay, I have a message I just need to check, see if it's something I need to answer right now. No, that can wait. Okay, so those are the units and the names of the electromagnetic spectrum. A couple of other terms you should be familiar with. We talk about light that is monochromatic and polychromatic. So mono in English, of course, means one, and chromatic means color. So monochromatic light is light that's only one wavelength. So like here, you see this prism. If we could pull out only the green, we might consider that monochromatic. Then we have poly, meaning many colors. So polychromatic light, that's light that's more than one wavelength. So white light is polychromatic, the light we get from a light bulb. We got all the colors are mixed in there. So these are just two terms you should be familiar with because we will use them as we look inside an instrument to see how it works. Monochromatic and polychromatic. Okay, so we said we're going to look at spectroscopy, and spectroscopy is interaction of electromagnetic radiation and matter. Okay, now remember last time I told you when I repeat something several times, you need to go, oh, that's important. Already I've said many times, spectroscopy is, so you need to know that definition. All right, so now we want to look at, okay, it's the interaction of electromagnetic radiation and matter. So how do these two things interact? Well, we've already looked at the electromagnetic radiation to say, what is that? And we said, well, it's a form of energy, but we think of it as being particles, these things called photons, or waves, and we looked at the equations that we use to describe those different natures. All right, now matter. What is matter? Well, matter are things like molecules, and atoms, and ions. And what are molecules and atoms and ions? What are those made of? Well, if we go deeper, we know they're made up of electrons and protons and neutrons. And we could actually go deeper and say, what are these made up of? But we don't actually need to know that for our class. This electrons, protons, and neutrons is enough for us. Okay, so when I say that electromagnetic radiation, the light, is interacting with matter, what it's really interacting with are these things. The most common one is actually the electrons. And that's actually the spectroscopy we will talk about. We will talk about the interaction with electrons. Now, how does electromagnetic radiation and matter interact? Well, there are three primary ways. It can do what we call a rotation, it can do a vibration, or it can do an energy level change. So we need to look and see what are these rotation, vibration, and energy level change. So the first one, rotation. So what that means is to turn around a bond axis. So you see it down here in this bottom picture. When you have a molecule that's rotating, that's turning around an axis, that's called rotation. Now, vibration, this is maybe different than what you think about. You know, you've all got your phones and you know you can put them on this mode called vibrate, where the phone goes, kind of vibrates. Now, that is vibration, but in chemistry or physics, that's not vibration. Okay? Vibration has a very specific meaning. It means a change in the bond length or bond angle. So you can see in these other pictures, you know, got the molecule. So if the bonds are stretching, getting longer, that's a vibration. Or the bonds are moving like this, that's a vibration. Or, you know, one gets longer and one gets shorter, that's a vibration. So that's what I mean by vibration. Now, notice that vibrations, note, and rotations only occur in molecules, not atoms. Okay, now, why? Well, go back to these definitions. Notice this right here, bond, bond, bond. Do atoms have bonds? No, they're a single atom. Okay, so an atom, you know, an atom can do this, vibrate, but it cannot do this definition of vibrate. So rotations and vibrations only occur in molecules, not atoms. All right, and then the third type of interaction, this is an electronic, it's an energy level change that we call electronic. Now, that electronic comes from the word electron, because almost always what you have is an electron that goes from a low energy state to a high energy state. Okay, it can either absorb energy and go to a higher energy state, or it can give off energy and go to a lower energy state. Now, notice this is electronic, it's not electric. Electric has to do with electricity. So these energy level changes are called electronic changes. Okay, and in this example, we look at it going from the ground state. Remember, the ground state is the lowest energy level, and then any higher energy state's called an excited state. Okay, so these three types of interactions that electromagnetic radiation can have with matter: rotation, vibration, electronic. Now, these are actually called transitions. Okay, so another word you have to know, transitions. So we talk about these three kinds of transitions: rotations, vibrations, and electronic energy level changes. And often to represent these transitions, we use energy level diagrams. We use these diagrams where we'll show, you know, a ground state, and then something getting excited and going to an excited state. Or something that's in an excited state can give off energy and come back down to the ground state. So just some words to make sure you know, so we can talk about absorption. That's the noun of taking in energy and going to a higher state. Absorb is the verb. Okay, emission is to give out. So emission is the noun, and emit is the verb, emitted, past tense, and then excited state and ground state. Okay, now let's look at an energy diagram for an atom. Atoms are quite simple because we said, okay, there's these three kinds of transitions: rotations, vibrations, and electronic. Okay, but an atom can only do one of those. Which one? Well, I said, remember, an atom cannot rotate, it cannot vibrate, no bonds. So atoms only have the electronic transitions. So we can use this energy level diagram. So we use E0, that's the ground state, and then we have an excited state, E1, and an even higher energy excited state, E2. And so the process is when an atom absorbs exactly this amount of energy between E0 and E1, it becomes excited. Okay, or it can emit exactly the amount of energy between E1 and E0, and then it becomes unexcited. It goes back to the ground state. Now, if a photon comes around and it has this amount of energy, that will not be absorbed because it's not the right amount of energy. So it only absorbs exactly the energy for its energy diagrams. Notice also that this energy from E1 or E0 to E1, and then we look at the energy from E0 to E2. Now notice, of course, this energy from 0 to 2 is a bigger energy, but notice shorter wavelength. Okay, remember that energy gets bigger, wavelength gets smaller. Okay, so for atoms, the energy diagrams are quite simple. We just have these simple lines, and it can absorb if it gets the right amount of energy between those two lines. Now, what about molecules? Well, molecules are more complicated because remember, a molecule has the same electronic transitions, which are the electrons going to higher energy states, but it also has vibration and it has rotation. So if we want to look at the total energy, we actually have to look at all three of these. And it turns out that the electronic energy, the energy for the electron to go to a higher energy state, that's always the biggest amount of energy. And depending what kind of electron you have, you may need X-ray light to excite that. You may need UV vis if it's an outer electron. And these will be our focus in this class. Now, vibrations, the energy to make something vibrate, remember that change in length or angle, that takes much less energy. That's usually energy that's in the IR range. And then rotations are the smallest energy. They actually only require microwave energy to make that happen. Okay? All right, so all three of these. Now, I've mentioned that different electromagnetic radiation has different amounts of energy, and they excite different kinds of transitions. Okay, I'm getting ahead of myself. Okay, yeah, all right, got my slides mixed up. Sorry, we'll come back to that point. All right, so molecules have all three of these, electronic, vibration, rotation. Now, we looked at the atoms and we said, oh, they have these nice simple energy diagrams because they only have electronic. But for the molecule that has all three of these, how do we make an energy diagram with all three of these? Well, molecule energy diagrams look like this. Okay, so over here is the atom, and then over here on the right is the molecules. And notice that the molecules are much more complicated than the atoms. Okay, because remember, the molecule has these electronic, vibration, and rotation. So let's take a closer look at this energy diagram. So first, electronic, that's the biggest energy change, is the change of an electron going from a lower energy to higher energy. So you can see here, this would be E0, right here. This bottom line, that's the ground state. And then E1 would be here. If we had an E2, that would be even higher, but this one only shows 2 electronic levels. All right, now we have the vibration, which is less energy. So we put the vibrations on top. So for example, this line down here, again, it's E0, but it's also V0. And then right here, this would be V1 and V2 and V3. Okay, up here, this is V0 for E1. And then this would be V1, V2, V3. So to excite electronic transition, I would need to absorb energy from here up to here. To excite a vibration, you would need to absorb energy from here to here, or from here to here. Okay, those are the vibration transitions. All right, now what about rotations? Remember, that's the smallest amount of energy. So we show those by those next set of lines. So this bottom line, again, this is now R0. And then right here, this guy right here, that's R1. And this one, R2. And this one, R3, R4, and so forth. And then so notice this up for V1, that's the R1, R2, R3, R4 for that. So to excite a rotation, then I need this amount of energy right there. Okay, so again, excite electronic, biggest amount of energy. To excite the vibration, this amount of energy. And then rotation, that small amount of energy. So for molecules, more complicated because we have these electronic levels, but on top of that, we have vibrations, and on top of that, we have rotations. So this is what a molecule energy diagram looks like. Okay, now where I was going before, I said, I talked about, we use a different kind of energy to excite electronic than we do vibration, than we do rotation. So this nice little table that's in your book and in your notes actually shows you what kind of transitions do you excite. So notice if I have UV vis light right here, which is our focus, that is the energy that can excite the outer electrons in an atom and in a molecule. Okay, if I want to excite the inner electrons, then I need X-ray light. If I want to excite things on the inside of the atom, the nucleus, then this is where I need that gamma, that very powerful energy. Okay, going the other way, if I want to excite a vibration, this is where I need IR, rotations, microwave. And then RF, these are actually exciting changes in the spin of things. Okay, again, for us, we're not even looking there. This is our focus this semester. We will not look at these other kinds of spectroscopy. We'll be looking at the kind where we use UV vis radiation to excite electronic transitions. Okay, now each kind of molecule or atom only absorbs certain frequencies. We say it's quantized. Now, what does this mean? Well, it means that the energy diagram for every atom, for every molecule is different. So if I have iron, iron might have an energy diagram that looks like this. And then I have lead. So this is iron. And then I have lead. Okay, lead will have a different energy diagram. And so, if I have light of this energy, I can excite iron. But for lead, I need this energy. Okay, that's what we mean. Each has different diagrams. Molecules, if you have benzene and cyclohexane, I really probably cannot draw either of those with a mouse, but we'll try. Okay, so that's cyclohexane and benzene. is this one, okay, those will have different energy diagrams. Now, they will all have electronic, and these have the vibrations and rotations and electronics. These just electronic, but the energies are different. So that's what this statement means. All right, now, when we are doing spectroscopy, the interaction of light with matter, okay, so let's just talk about the absorption of light. We're actually going to measure the frequencies or the wavelengths that are absorbed, and we're going to measure the intensity, okay, and we get this thing called a spectrum. Okay, if you have more than one, it's a spectra. So two more important words for you to know: spectrum and spectra. So the intensity tells me about the degree to which a frequency is absorbed or emitted. So a spectrum, let me clean up the slide a little bit and then we'll, so much easier with a chalkboard. So a spectrum is also a plot. Now, this is not a calibration curve, this is a spectrum. So a spectrum, over here you have intensity, and here you have wavelength or frequency. Okay, usually for us we'll be doing wavelength. So you get this plot, and for a molecule it'll look maybe like this. And this plot is called a spectrum. If I have more than one, it's called spectra. All right. Now, the intensity tells me how strongly it absorbs something. Here we're doing absorption. You could also do emission for these. And the intensity also is unique for species. So, this might be the spectrum for one species. Something else will have a different spectrum. It might look like that. Every species has its own spectrum. And we can use these spectrum to identify chemicals. We can use these spectrum to answer the questions: what is it? That's mostly for atoms. And how much is there? Okay, so we said spectroscopy is the study of electromagnetic radiation and matter. Spectroscopy is also the study of spectra. It's the study of these plots of intensity versus wavelength. So here, for example, is the spectrum for benzene. So notice that here on this axis we have intensity. This is probably absorbance that's measured. On this axis, we have wavelength. You can't even read that. Oh, that's bad. Okay, so notice, it has the highest intensity here. So that's what a spectrum looks like. One example. One quick note, look at this axis here. It doesn't tell you the units. Any guesses what the units are? Remember, I told you that this semester we'd be looking at UV vis. So this is actually in the UV region. And the units here are actually that angstroms that I talked about. So this is actually from 200 to 300 nanometers. But this is an older spectrum, so they're using that angstrom unit that I mentioned. Okay, so that's kind of a quick introduction to spectroscopy. I am actually going to stop there for today. So let's talk about your homework a little bit. All right, so your homework, first from chapter 1, you need to do question 8. And you need to do questions 1 and 2. Okay? And so you should do all 3 of these on RAIN. For those of you that are retaking the class, you're not in the RAIN classroom yet, but they have added you to the official list. So I'm hopeful you will be in the RAIN classroom soon, within the next few days, I hope. Okay, now for these questions, these are all calculations. So remember, for calculations, you need to show me how you get your answers. You need to give me the equation, and the numbers that you use. Now, the one exception is in question 8, you have to calculate an average and you have to calculate a standard deviation. You do not need to show me how you get these. You should know how to use your calculator to do these. So just use your calculator, and on your paper you can just write x equals whatever, s equals. Okay, these you do not need to show me the equations. Just use your calculator. Do remember that after you do these on a paper, you're going to write them out. You're going to take a picture. Anytime you give me a picture, you need to have your name and your student number on the picture. All right, so that's your first part of your homework, is to do those on RAIN Classroom. You also need to look at all of the questions for Chapter 1. Okay? Remember I told you the first day, you always have to know every question in the book. Now, you don't need to give them to me. I don't want you to give them to me. I've given you the answers to those questions, but make sure you understand all the questions in the book. Okay, second thing for your homework is to take a practice quiz. Because we're going to have quizzes on RAIN, I want to make sure you're comfortable using it and the different kinds of questions. Okay, so there will be a quiz at the end of class posted on the RAIN. And there's every kind of question that you might see on an exam or quiz will be there, and we'll talk about each of those. Now, this quiz is timed. It's 10 questions, and you have 30 minutes. Now, you don't need 30 minutes. It's very easy questions. It should take you 10 minutes to do this quiz. So you don't need to study for this quiz. You don't need any special knowledge. And in fact, if you get all the questions wrong on the quiz, it's okay. It's just to practice. So you need to do it, but you're not going to get a lot of points for this quiz. And you get a point for doing it, but nothing else. All right, so once you start it, you have to finish it because it starts timing you. And if you think, oh, I'll start it and come back in an hour, you won't be able to finish the quiz. So you need to do it all at one time, which will be the way your regular quizzes will work. Okay, so what kinds of questions will there be? Well, there's multiple choice and true, false, and matching, and short answer, and calculation. So let's look at each of those. So first, the multiple choice, there's two kinds. There's a single answer, which means there's only one right answer. And most of the time, this is the kind of multiple choice you will have. There will also be occasionally a question that's a multiple answer. So then you have to choose all of the answers that are correct. These are much harder questions. So for these, maybe 1 is right, maybe 2 are right, maybe 3, maybe 4, maybe all of them. So you have to really know what you're doing for those. And I won't use a lot of those, maybe once in a while, but we won't have a lot of those. Now, notice that I've got the Chinese for these because the system will show you the Chinese. But if you don't recognize the Chinese or remember the Chinese, it's okay. Because I will, if it's a multiple answer, I will always write in English, choose all the answers that are correct. If I don't say that, then choose one. The other kind you might have is true, false. Now, again, these are going to be in Chinese. But it's okay. The question will say true, false, and give you a statement. And I think everyone can understand this and this. This means true, and this means false. Okay. So really, you don't have to understand the Chinese to be able to answer these. All right, the next kind, the short answer and the matching. Those will always, in Chinese, they always say that they're this kind of question. That just means subjective, and that's not important. So again, you will, from reading the question, you will know what you need to do. So short answer will just ask you a question. Like one of the questions on the quiz is, what time should be what time do you plan to take the quizzes? And you're going to tell me, if you're in China, you're going to tell me 8:30. If you're not in China, you can tell me which time. Okay, so short answer. Now notice for short answer, you don't need a complete sentence. All you need to do is give me the answer. All right, the next kind is matching. So the matching will always say matching. And these are maybe the hardest because you have to write the answer, you have to type the answer in a box in a certain form. I always want your answer to be, like 1C, 2A, 3B. So I have a little example right now of matching to show you what I mean. So here, match the animal to its descriptions. And so notice that not all the choices will be used. So it says, 1, the biggest animal listed is the, so you look at the list, so you're going to say, okay, so your answer, you're going to write 1C. Okay, and then the next one, 2, the smallest animal listed is 2E. Okay, and then the blank is native to only China, so you're going to write 3. Okay, so I'll just show you 3D. And let me get rid of my writing so you can see that. 4A. So this is how you're going to write your answers for matching. Okay, there'll always just be a box, and you're just going to type in, 1 in your choice, 2 in your choice, 3 your choice. Okay, so quite simple, really. Okay, and then finally, there will always be calculations on your quizzes, math problems. Actually, I think we have one quiz that won't have calculations, but if you do have calculations, these will be the instructions. So first, you always are going to do these by picture. You're going to write it on a piece of paper, and you're going to take a picture with your phone. And you always have to have your name and your student number on the paper, just like for the homework. Okay, and just like for the homework, you show me your work. You show me the equations and the numbers you use. If you don't show me all your work, then you're going to lose points. Then you clearly indicate your final answer. Remember, you do that by you put a box around it. And if you need units, you need to have them. And always, always watch the significant figures. Okay, so those are the rules for calculations. I always have to be able to read your answer. If you write so messy, I can't read it, or if I can't tell, is that number, what is that number, then it's wrong. And again, pictures have to be handwritten. Maybe some of you want to type them on your computer. That's not okay. For calculations, you have to write them out by hand. And you need your student number and name, or you get a 0. Okay, so that's the practice quiz. So for your homework, you need to do those 3 problems on rain, and you need to do the practice quiz. Now, next week is a holiday, so these are due in 2 weeks by the beginning of class. So next week there will be no class. We may have to make the class up later because we have 2 holidays and we have too much material, but we'll see. For now, next week, no class. And then next week, so 2 weeks from today, we're going to finish chapter 2 and start chapter 3. So next week, please bring a calculator to class. I'm going to give you some calculations I actually want you to do in class. They're important calculations that we need to make sure you know how to do. Okay, so that's what's coming up. And if you were one of those students at the beginning and I'm still missing your student information or your attendance from week 1, it's very late. I need to have it as soon as possible. Okay, I think, yep, that's it for today. Okay, so we'll go ahead and stop there for today unless there are questions. So any questions?
Do we have a attendance for today or?
No, I will take attendance once in a while. I'm not going to take it every week. Mostly I'm going to leave you alone and let you be adults.
All right.
Any other questions?